Some of the toughest physics problems can look, well, deceptively simple on the page. Today, we're going to crack open a classic from the legendary Irodov textbook. It's a problem that really makes you think about what force actually means when something's moving. So let's break this thing down step by step.
Okay, so here's the problem. Number 1.120. You've got a particle moving in a circle. But here's the twist. Its kinetic energy isn't constant. It's actually increasing the farther it travels, based on the formula T equals A times S squared. In plain English, it's speeding up. Our mission is to figure out the total force acting on this particle as a function of that distance, S.
All right, so where do you even begin with a problem like this? Your first instinct might be a bit of panic, right? The kinetic energy is changing, which means its speed is changing, so this isn't that simple uniform circular motion you see in Chapter 1 of most textbooks. So how in the world do you find the total force when both the speed and the direction are changing at the same time?
Well, the key, the absolute secret, is to realize that the total force is actually doing two different jobs at once. And because of that, we can split it into two separate parts that are perpendicular to each other. One part is in charge of changing the speed, and the other is in charge of changing the direction. And that's our strategy.
Let's get a picture of these two forces in our heads. First, you've got the tangential force. Think of it as the gas pedal force. It points along the path of motion, and its only job is to make the particle go faster or slower. Then you have the normal force. This is the steering wheel force. It's always pointing toward the center of the circle, constantly yanking the particle sideways to keep it from flying off in a straight line.
So our roadmap from here is actually pretty straightforward. We're going to tackle this in two steps. First, we find the tangential force. Second, we find the normal force. Once we have both of those pieces, we can just combine them to get our final answer for the total force.
All right, first up, the tangential force. So the big question is, how does a force relate to a change in kinetic energy over a distance? Well, this is where the work-energy theorem becomes our best friend.
You gotta remember, only the force component that's in the direction of motion does any work to change the speed. So if you think about a tiny little chunk of work, dW, it's just the tangential force times a tiny little distance, ds. And that work has to equal the tiny change in kinetic energy, dt. If you just rearrange that idea, you get this incredibly useful formula. The tangential force is simply the derivative of the kinetic energy with respect to the distance. It's the rate of change.
And with that powerful little formula, this step becomes honestly super easy. We were given that T equals A times S squared. All we have to do is take the derivative of that with respect to S. The derivative of S squared is just 2S, so, boom, our tangential force is 2AS. See? Part 1 is already in the bag.
Great! One down, one to go. Now for the second piece of our puzzle, the normal force. Now to get this one, we first need to get a handle on the particle's velocity.
Finding the velocity is pretty straightforward because we have two different ways of looking at kinetic energy. We have the classic definition, T equals 1/2 mv squared, and we have the one the problem gave us, T equals as squared. Since they're both equal to T, we can just set them equal to each other. A little bit of algebra to solve for v squared, and we've got an expression for it. Notice we don't even need to take the square root. Just finding v squared is all we need, and that's going to make our lives easier in a second.
Okay, now we can pull out that classic formula for normal force. You might also know it as centripetal force. It's Fn equals mv squared over r. This is the force that's constantly pulling the particle toward the center, the force that's required to make it turn.
And now it's just a matter of putting the pieces together. We take that expression for v squared that we just figured out, and we plug it right into the normal force formula. It's like fitting two puzzle pieces together perfectly.
And what's really satisfying here is that the mass m on the top and bottom just cancels out. It leaves us with this nice, clean expression for the normal force. Fn equals 2as squared over r. And just like that, we have both of our force components. We're ready for the final step.
We are on the home stretch now. We've got our tangential force and we have our normal force. It's time to put them together and find the magnitude of the total force that's acting on our particle.
Now here's the beautiful part. Because the tangential force and the normal force are always perpendicular to each other, they form the two legs of a right triangle. The total force? That's just the hypotenuse, which means we can find its magnitude with a tool you've known for years, the Pythagorean theorem.
So let's plug in what we found. The total force, F, is the square root of our tangential force squared plus our normal force squared. And yeah, I know, it looks a little bit messy right now, but trust me, we can clean this up. If we look closely, we can factor out that common term of 2as from underneath the square root. And when we do that, we arrive at our final, elegant answer. The total force is 2as times the square root of 1 plus the quantity s over r squared. And there you have it. That's our complete solution. We did it.
Now look, getting the right answer is awesome. But the real takeaway here is the strategy we used. Understanding the method, and more importantly, understanding the common traps, that's what's really going to help you solve the next mechanics problem and the one after that.
So what are those common pitfalls? The absolute biggest trap on a problem like this is completely forgetting about the tangential force. So many people see circular motion, and their brain just screams F equals mv squared over r. But remember, that's only half the story here. That's just the normal force. The other big mistake is not realizing that super handy shortcut, that Ft equals dt by ds. If you remember to split the problem into these two components from the very beginning, a really tricky problem becomes totally manageable.
So that was Irodov 1.120. But this whole strategy, this idea of breaking a force vector into perpendicular components that each do a different job, is one of the most powerful tools you have in physics. Seriously, think about it. How could you apply this to, say, projectile motion? Or maybe an object sliding down a curved ramp? It's a technique you can use again and again. Thanks for working through this one with me.